Testing. Testing. Supply. I hope that's okay. Any question before start, please feel free to ask. It's 2 minutes before start. Một mình thấy you can always focus. You can always focus. Đi vô đây này học cái sân thì họ đi thi người ta cả đi vô chỉ là học A and B là so is the mic working? Not really. Okay, this seems to be. Okay. So, I guess we can start. The goal today is to finish this thing. Probably we'll continue talk about the content distribution, talk about normal and their friends. And also talk about Excel. Excel will be very brief because basically we will tell you how to do the shortcut calculation based on Excel function. So nothing really deep here. Okay, but today is very important because we need to know how to use Excel and also the normal distribution. Okay, so very quickly, we review what we are doing. Some admin thing probably. Probably I'll announce. Probably we'll cancel we'll reschedule the next Wednesday class because we'll have a class in the B.B.A lab. It's optional because some of you mentioned want to do one I taught about R, and many of you actually bring the lab iPad, so which make us cannot teach easily. So that's why we will reschedule that class, probably another as well, to the B.B.A lab. So that's the optional. You can learn those software programming probably at the end of the semester because we want to teach everything at the end because once we taught everything, then we cover the programming at the end. But that will be optional as well. So probably we'll cancel the next Wednesday class. But anyway, let's get started. I shouldn't say cancel, it's like reschedule, but anyway, it's optional. So random variable, the idea is, as I emphasize again, is we are talking about assigning numbers to outcome. The reason is because we often measure uncertainty, right, by numbers, right? Then that is the random reason. And second reason is to make our life easier, right? Because of the sample space can be substantially reduced, and a lot of application requires actually numbers. So that is the reason why we focus on numbers instead of working on the event or outcome by themselves. And there are, depends on what kind of number you can put, right? Either will be discrete or continuous. Say for counting number by natural numbers, then naturally you have discrete, right? Number of customer arriving, number of defective product, so on and so forth, right? These are very naturally discrete. But when we talk about money, profit, prices, temperature, other thing, continuous would be a more appropriate, right? Because continuous, what it means is, in general, is decimal numbers, right? And usually prices usually modeled by decimal numbers are more appropriate, right? So very quickly, I'm not going to review everything because we have done so many times. So I will start the review from continuous distribute continuous random variable. So I add some slide here, but it just repeat what I said. For continuous distribution, we cannot use the px. One the reason is because of continuous means that many possible number, right? And if you have infinite many, and if many of them has probability more than 0, you add them up, it will be more than 1, right? So by construction, it's necessary that most of them actually have probability 0, right? So that means that Px is not a well-defined concept here, but f of x is still a well-defined object here. And if you recall, the example I have said is, suppose a uniform two outcome, right? The mass is equally likely, the f of x is like stacking the p, right? If you increase to 3 of them, you can easily you can see the same, right? You can see this if I increase to n outcome, I still have the same graph, right? No matter how you do it, it's like upward sloping for the f. But the p is an issue. If you have many outcomes, the height of the bar for the p will shrink to 0 because this is 1 over n, right? You have the many outcome, then there's no more height, right? So you cannot use p of x to describe continuous random variable. So the technical issue here, right? And this is what I said. So the technical issue is you can define f of x, okay? And one thing I probably have to add explicitly, of course, I also write down on the whiteboard, is how you can use f. This is the basic thing, is you can use f, right? F by itself is telling you the probability that less than that, right? When very often we were interested in probability that the random variable between A and B, okay, you will be just FB minus FA, and bigger than B will be just 1 minus FB. So this is the complement rule. So these are the things that we often use for our calculations, because we don't do integration and we all often work with F. So this is the two formula that we often use. And because some of you actually ask me, okay, how can we understand the small f without looking at the limit or differentiation? So let me define that. You can imagine for some number, B and A is very close, okay? That means that the probability between A and B, okay, will be just the interval, the length interval, times f of x, okay? X is being some number between A and B. Okay, so it is what it means. It's like the probability. It's like density, right? Because it's like the length you times the height, right? So that is like fx is like the height of the bar graph, right? Or you can say for x is between x and plus delta, right? The probability over the size of the length then is the f of x. So that's why it's called density. Okay, but that is the definition. Of course, you can go back to the calculus. This is the how we define, but I'm not talking about calculus. Okay, in the case where how you would utilize the small f to understand is usually the pie graph, which we'll use for the rest of the class. Okay, and imagine this is the small f. This we also, you can see this as a bell curve. Usually later you see today is a normal. We often work with this for the rest of the class. And a number A, right? And by the meaning of F means that the area on the left-hand side of A is the big F. Okay? And the area on the right-hand side is 1 minus FA. The reason is the whole thing must be 1, right? This is the probability. Okay? Area under F is probability. And if you want something in the middle between A and B, it will be just FB minus FA. So this is the graph, don't worry, we use it. I just put it here. I already said that in the whiteboard, but I just put it there because I don't want to draw it again when I review it, right? So, and expectation is the same idea. But if you look carefully, everything actually follows from the idea of taking limits for the summation, you get integrated. But I'm not going into those ideas unless you are a QFN student. Then probably you need to worry about this because not in this class, but when you go further, you will be doing this kind of problems. Okay, but it's not a concern for us. Okay, so let's quickly review uniform and exponential. We'll dive into normal, which is the goal of today. Okay, so uniform. By construction, same as what we have seen in the discrete case, right? Discrete case uniform, we're saying that each number in the support, right, is equally likely, right? Like rolling a die, 1 up to 6, each one have probability 1/6, right? But when you're continuous, it's not easy to see how it translates, right? But you can imagine that the probability, the small f is flat. Right, because remember, small f is similar idea to the big P, right? But it's not probability, but it means something. But it means density. It's like times the interval gives the probability, right? That's the idea. So that's why the graph of f looks like this guy, a horizontal line, okay, flat one, okay, and the height is restricted by b 1 over b minus a. The reason is being the area under F is the probability. The whole thing must be 1, right? And the base is B minus A, right? So by construction, the height must be, okay, 1 over B minus A, because when you multiply, it's 1, right? Because you learn the primary school, right? The rectangle, right? Must be the base times the height. Right, it's the area, and the area is 1. Okay, that is the area. Okay? This is the only f we want to discuss. Okay, for the calculation. For the rest, we're not going to discuss the f. Okay, we show the shape, but we're not going to discuss it because we want to talk about this because this is you don't want to understand why it must be 1. What's the meaning of under f? Okay, and don't worry, it's not math class. Just to give you some idea. Okay, I'm not intended to you to know how to do the calculation, but mainly is we will work on f most of the time, right? And f is, remember, is the probability that x less than or equal to x, right? So which means that if I have x here, what's the height? Height is the probability less than or equal to that, right? And that is coming from the idea if I have X here, right? What's the probability less than or equal to that will be this area, right? This is the area, and this area exactly the probability that the random variable less than or equal to this number X, right? And you learn from primary school, rectangle again is just the base time height, right? What's the base? Base is this distance, which is X minus A, right? And the height is already given B over A, right? So this height will be X minus A times 1 over B minus A, right? So this is the formula that why you get from the previous slide, right? And that is the formula that you'll be using for all calculation. I'm not expecting you to know the F, small f, but the big F you need to know. Not remember, but you need to know that represent the probability less than or equal to that number. And that is the thing we use in example and all the assignment, right? It's something I expect you to know. I don't expect you to know from small f to big F. Okay, it's good to know. Okay, the reason why this is true. But the thing I need you to know is how you use the big F, apply the calculation, and that's what you need, right? Because remember, when you are given a discrete random variable, all we need to know is the big P. For continuous, what we know is the big F. And big F tells us everything, right? Because we're asking the probability between certain interval, right? With the big F, we know everything. So just to, but I want to let you know how you transform to small f and big F, right? The reason is small f tells us the area under the curve, and that is helpful for all the calculation. Later you see when you calculate normal, everything is, we look at the small f, things become cleaner, okay? But the calculation wise, the big F is the thing we need, okay? So there's some conceptually we use F, okay? And for calculation wise, use the big F, okay? So it's a little bit, the mind a little bit have to be able to go from two worlds, small f and big F, okay? Small f is for conceptual understanding, big F is for calculation, okay? So later, don't worry, we'll be using this kind of thing for the rest of our course. So you will know it, okay? There's no way you can't know it. Okay? If you don't know it, then you'll fail the exam for sure. Because this is something that we use for the rest of our class, okay? Now, there's some slight changes to the slide because I want to add the first few bullet points to make sure that you know what we need. Okay, I just put there. There's no change in the slide, but just simply add the information there. Oh, maybe I should forget about the integration. There's something I need. Okay, so for uniform between A and B, you know the F because F is a thing we need, and why we need to also know the mean and variance. Same idea when you learn topic 1, right? You give a data, how to represent data. If you use two numbers to tell people the mean and variance, the same idea. If you're given distribution, of course, F is the complete description of what we should know about that. But if the boss want you to ask, okay, what can we know about this? It's the mean and variance, right? Because mean is telling us what you expect from that if you do it enough time, right? And variance looking at how variation of how spread about this means, right? So I'm not going to explain the derivation unless you are QFN student. You need to know how to derive that, okay? Not in this class, but in the future, you need to know how to do the integration. Okay? You will involve some integration by part if you actually do it, but anyway, not our concern. The example of this will be, okay, so you are observatory, right? And you know it's under the black rainstorm or the red rainstorm, right? Then the question would be, what's the rainfall, right? The historical data is from 1 mm to 4 mm, right? Without good information, then uniform would be the right approach to do. right? I mean, unless you're observatory, you're supercomputer, right? If you are the business owner, right, you're selling umbrella, then this is what you expect, right? Or you want to see whether you want to put a barrier in front of your shop, right? So on and so forth, right? Then you could look at the mean and variance will be the thing you want to see, right? And then probably the next question is how are you going to do based on mean and variance, right? And that is beyond the scope of class, right? Depends on what you need to think to do, okay? And I think the probability will be most useful one because that tell us what might be done, right? You can tell the probability between 1 and 3, right? The way to do it, as I have mentioned, is look at from 1 to 3, right? It just this guy, right? F of 3 minus 1. The reason is for continuous, with the equal to has no bearing. Okay, so although F is mean less than or equal to, right? And these are the same. Okay, and probably we have to be a little bit more careful about whether 1 or 3 are inclusive. Okay, but in our class, continuous is truly continuous. So whether equal to or less than doesn't really make a difference. Okay, for our class. But for QFN students, have to be very careful. Where equal to can be more tricky when we call mixed distribution, combining discrete and continuous. But for our class, we are not going to that deep. So when continuous, it's always continuous. There's no mass there. There's no equal to. It's always 0. Probability for particular point is always 0. So that's not an issue for our class. So we are being loose on the terminology here. Okay. Anyway, so you can see the example between 2 and 3. We will do in the same way. Either you can apply the F function, or you can look at the small f and calculate area. I'm not going to repeat for that one for the time. So next one is something I guess would be one of the very useful modeling tools for learning from this class, and usually is have a lot of application when you study advanced classes, not limited to probability, but this is a very useful one because looking at how long does it take for something to happen, right? This is something that modeling for the time, right, is why continuous would be appropriate one. It's asking how does it take for something to be successful. Okay, you can imagine this Poisson, right? It's the time that for things to happen, right? And you can prove, but it's not our goal. Is you can actually prove the time is actually follow this one. Actually, you can prove it using the Poisson idea, okay, and can link to this guy, okay. But it's not a goal to explain this. So this just take a moment of faith. This is what you get when you look at the Poisson, and this is what you get. Okay, but it's not the goal. But what you need to know, actually, we show in the next slide. This is the formula we need to know. Okay, and lambda will be on average how many people would arrive. Okay, how fast it is. Okay, so let's see the example. Probably will give you idea what do you mean by that, and example will illustrate how we use them. Okay, and remind you that it's natural to see why you have mean is 1 over lambda and lambda squared, right? Because imagine that in an hour of time you have 2 customers come in, right, on average. So what is on average the time that 1 customer would come, right? 1 hour you have 2 guys, right? So you expect every 30 minutes you're coming a guy, right? So how long does it take for 1 guy to come? It's 30 minutes, right? It's exactly 1/2 of the hour, right? So that's why 1 over lambda. But do you notice the mean is no longer same than variance at this time? Okay. Remember for Poisson, mean is same variance, but here we don't. Okay, and we don't explain why. It's just for integration. Okay. And would like to show you look what the f looks like. That's why it's called exponential. Is that the density actually drop down, right? So this means that it's very likely that things would happen. Look at the red one, is 0.2, right? 0.2 means that the mean is like 2 here. Okay, so it's very likely that a lot of things can happen in the beginning, right? But if a very long tail, right, and the tail is infinitely long, that's no ending, right? And where 1/5, the red one is 5 here, right? So mean is here. And for the blue one, 1/2, so it's 2 here, right? So it's just like most of them actually a lot of them is here, right? So a lot of them are actually the beginning. Okay, a lot of things happen at the beginning. But this is the shape. Just that's the name you call exponential, right? It's exponential curve. If you learn physics, okay, nuclear physics, right? This is actually the nuclear atom nuclear reaction, right? The time for things to emit, right? If you learn that, but anyway, it's not physics class, so I'm not going to talk about this. But this is a lot of application in physics. But anyway, we are business school, right? So we don't care about physics for the moment, at least for most of our application. But this is very useful. Okay, so let's look at this example to give you the idea. So this is very common example. Suppose time for next common derived for an exponential mean 20. Okay, how do you do that? Look at historical data, right? How much time you can wait for one customer to arrive, right? And this gives you the idea how you do the modeling, right? So to remember the idea of this class or this topic is trying to give you a model that to understand the future, right? Because probability, right, is a language to talk about future. And how to talk about future? Not by a wild guess, but educated guess, right? How you get the educated guess? From data. The data you obtain from the historical business, right? How you do look at the data, how much time you wait, right? This is the way, okay? And here the question would be, what's the probability that a customer arrive in 10 minutes? Okay, and all right, so that is the thing. How to do the calculation? Okay, so first you have to be look out to describe an exponential distribution. All right, you need to know the big F, right? And the big F, the only thing that you need is the lambda, right? And you know the mean of the exponential is 1 over lambda. Okay, then that's why 20 is equal to 1 over lambda. That's what I written here, right? Because if you look at the formula, right, exponential is lambda inverse, right? It's 1 over lambda. So that means that lambda is 1 over 20. Okay, is that okay? Then what we're going to do is the probability that arrive within next 10 minutes, so less than 10. Okay, and that is exactly f of 10. And just put in the formula, which we expect you to know, right? This guy, right? 1 over 1 minus e to the negative lambda x. Okay, we just plug in x is 10, lambda is 1 over 20, then you get the probability. Okay, of course, if you ask what's the probability that is more than 10 minutes, right? Then just 1 minus the answer, right? Then let me say it out explicitly, right? So if you are asked, if the question asks you more than 10 minutes, right? More than, right? Then just the probability that x more than 10, right? But this is just 1 minus f of 10, right? And you know how to do the calculation. I'm not going to repeat that, but that is something that you would be able to do that, right? So that is very often this kind of question is being asked, right? Because you need to know when someone will come in, right? And make a decision, right? How you deploy the staff, so on and so forth. Is that okay? Maybe I should give more example. Let's see. Do I have any more example in the slide? I don't know. Oh, I have one more. So this is a little bit trickier, but shouldn't be a big thing. We're asking you, given the same model, but we ask a little bit more trickier question. Instead of asking more than 10 or less than 10, we ask 5 and 15. Okay? Why you want to care about that? Maybe a staff want to go to washroom, right? You give him 10 minutes break, right? And that is the thing. I don't know. For some reason, I mean, this is the case. So calculate that probability, right? And you can easily see that between 5 and 15 is just exactly this question, right? And it's clear that between 5 and 15 is just f of 15 minus f of 5, right? Just to remind yourself why this is true. This is probability that x is less than 15, right? And this is probability that x less than 5, right? And this is what it means, right? 5, 15 minus 5 is 5 and 15, right? And this is just addition rule, right? Because this addition rule, just to remind you why the addition rule, because this plus right? This is the addition rule. There's nothing new here, right? So I hope you should see, right? And probably some of you from QFM will say, oh, why equal to and equal to doesn't matter, because for truly continuous, equal to 5 is probably 0, right? Probability that x equal to exactly 5 minutes, 0, right? Because they can come in at 5 minutes 1 second, 5 minutes 2 seconds, 4 minutes 59 seconds, right? So there are many things next by 5. So the point exactly 5 is 0. So that's why that's the same. Is that okay? And just put in a number, you can do the calculation. So some of you still worry about inputting this, but Excel formula we'll talk about today give you all the answer directly. Okay? Is that okay? Is that okay? Any question? Now, just not going into detail, but give you some idea why we need that, right? Say, for example, the service time. How long does it wait for someone to come? Equipment failure. How long does it take for things to fail? Right? And inventory management, that is, I think that's the most applicable thing, right? Because probably, right, a lot of things now is just in time, right? You don't keep extra inventory in your store. Then probably you need to think about how to order stuff, right? That would be exponential would be the important. And the next one is project management, right? And you would be very important. You expect how long does it take for the software bugs to come in, how to deploy your stuff, right? So and so forth, right? And how long does it need to wait for customer to feedback, right? Because look at the thing now, right? You just try to use the chatbot to ask for customer service. They will tell you how long does it take to wait for the next guy to serve you, right? It's exponential, right? And that is how they come up with, oh, the current waiting time is 5 minutes, or the current waiting time is 10 minutes, so on and so forth, right? These are the way they generate the answer for you, right? Assuming things are exponential, which usually is fine. Okay. And not going to go to detail. If you want, you can just go and read that, but I think it's straightforward. So here comes to the most important thing of class, okay? The only thing that probably, no matter how long you start after this class, the only thing you remember at least is the bell curve. The normal is the thing that you will never forget. It can be in your group dream, can be in your nightmare, but this is the thing that you'll be doing. It's called the bell curve. Okay. And first is the support. Bell curve is the no limit, can be any negative number, can be any positive number. Okay. So it is convenient, so there's no endpoint. Of course, there's also one drawback is something you cannot be negative. Right? Look at the price of the stock, it cannot be negative. Right? So how do we do that? Usually there are two ways to answer this question. One is you don't model the price by itself, you model the return, stock return. And stock return, you can plug that in, there's no problem. Right? Because the return can be negative, positive. Second is later you will see it is, although it's negative infinity to positive infinity, but it's a bell, do not have big variance, which later we see. Everything actually follow within 2 SD or 3 SD. Okay? As long as the SD is not huge, there's no problem at all. Okay? So that's not an issue unless for many applications. So that's not a big deal. And although the name is called normal, turn out that the small f and big F is a monster. If you call, actually integration actually don't give anything. Okay, there's nothing I can write further. This is the formula, so cannot be even expressed in math. Okay, that's an expression. Okay, and you have to look at table or look at the calculator. Okay, there's no closed form solution, and even the small f is look ugly. Okay, and I still put here because this is the thing that we study, so I have to put there. This is the main object we want to look at, and doesn't matter even though if you don't follow. I mean, most of you would not be able to follow it, but you have to try to familiarize the phrase with this f, and this small f is actually a bell curve. Okay, and if you can easily try to envision this, is basically the binomial, right? Which we have a formula, and this one, if you take n to be very large, you will end up with this kind of stuff. Okay, and usage of normal, okay, by the name means normal means very common. Okay, look at IQ, look at weight, look at height, look at a lot of things around us is actually normal. Okay, and we'll talk some of the reason, probably 2 topics later. We'll talk about central limit theorem, which essentially basically said if what we observe is actually an outcome of many stuff, okay, and that will be a normal. Okay, for example, IQ is determined by a lot of things, right? What kind of food you eat, what kind of education you have, what is your parents' education, what DNA, so on and so forth. It's determined by many stuff. So that's why normal. Same as weight and height, right? Weight and height are determined by the genes, determined by environment, right? And some of you may believe these are related to the stars in the universe, right? Because they look at what to do is look at whether does cosmology actually have an impact, right? So the same, right? Because so these are the things that you think they are relevant, right? So let us quickly go into the application part because this is the main thing of the class. Okay. So as you can see, even I forgot to mention is the main thing about this formula, right? We have something interesting with the exponential, which is 2.713, and we have pi, right, which is the common thing 3.13. Okay, although they're crazy stuff, but fun thing you have to look at is we have a sigma in the mu, okay? As you may expect, mu is the mean, sigma square is the variance. And these are the two parameters of the model, okay? Just like binomial with n and p, hypergeometric with big N, small n, a, okay? Exponential with lambda, uniform with a and b. And normal, we have mu and sigma square, okay? And mu and sigma square determine the mean and variance, right? And let's look at the graph, okay? And that's exactly what I mean, okay? Look at the red one, okay? First, mean is 0 means the bell, the peak of the bell is actually at 0, okay? If mean is -4, the peak of the bell is -4. If mean is 0 green again, the peak is also at 0, okay? So mu control the location of the bell peak, okay? The second is the variance. Variance determine how spread out or how tall is the bell, okay? And the bell is, compare this case, red and the green curve, right? The red curve has variance of 4, so it's much flatter than the green curve. And do remind you that why it's flatter, because the area under the curve is always 1, right? Because the area under this f, because we're drawing small f, right? So this is the area under is 1. So if you have much larger variance, right, as a red curve, you can see it's much spread out, right? Because variance, right, spread out. Is that clear? So this is the graphical representation, okay? And basically this is what we need for the rest of our class, mostly. Okay? So the normal will come back very often, and later you will see why. So this is the graph that the point that you want to look at. I add the first 2 bullet points compared to your slide, but there's nothing different. I put there because I try to be consistent in the style when I introduce probability, okay? And you don't need to know the F anyway, but I just put there because I think we use normal all the time, so it's good to, when you see this is the thing that we want to have, okay? And there's some minor thing is symmetric, okay? Left and right the same, okay? And the skewness is 0, okay? It's symmetric, right? Because that's how it's being proved. And kurtosis is always 3, okay? So just to remind you that kurtosis always, when you look at stuff, it's always compared to normal. Fatter than normal is called fat. Thinner than normal is called thin, okay? It is the guideline that we're looking at. Reason, normal is so common and almost everything is normal, okay? So because normal is so useful and so convenient, we need a shorthand notation for normal, okay? And if we say x is a normal distribution with mean mu and sigma square, we write this as x. If a snake here, the curly snake is you should read it as is distributed as, okay? Or has a distribution, or follow the distribution, okay? So that's what I mean, okay? For the distribution of normal with mean mu and variance sigma square, okay? This is the notation we use all the time. One thing that is only true for normal, okay? Not true for other thing is a linear property, okay? Actually turns out to be very convenient. As you can see, if I have a random variable which has followed normal distribution, and I multiply by constant A plus a constant B is still a normal, okay? The only thing is I basically change, okay, to this one. This one is actually we learned before, right? Because remember, expected AX plus B is what? is A expected X plus B, right? And variance of AX plus B, right, is A square variance of X, right? So this is just, you just replace this by sigma square, and this is just mu, right? You get this formula. Okay, there's nothing deep on the right hand side, but the important part is the normal, you multiply and add things, is still normal. Okay, why this is important? This is important because our life will be way much easier, right? Suppose you try to model stock returns as a normal distribution or stock price. Okay, if the one stock, the price movement or the return movement follow normal, okay, the one stock. It also means that your portfolio, right, including a share of stock, it still can follow a normal distribution. It's the bell curve. Okay, so it is not true from all the things we learn, right? If you have a binomial, you cannot add things to binomial, right? Because binomial is start from 0. You add things is not binomial, okay? And similar to others, you multiply, add, it becomes another stuff, right? Because the distribution is the shape of the bar plot, right? And you subtract or multiply stuff is no longer what we want to be, okay? But the interesting thing also very true is normal adding or multiplying is still normal, right? This is super important. You will see in the next slide why this is important. The reason is, okay, in this one, later, let me show it to you. It's what we call standardized normal. The reason is, for one normal, you have mu and sigma square, right? So for different mu and sigma square, you have different type of bell curve, right? And your life will be difficult, right, to understand so many bell curve. But what it said is, you don't need to look at many bell curve. You just need to focus on one bell curve, okay, which is called standardized normal. You can always make A 1 over lambda over sigma, B is mu over sigma. Then when you do this transformation, standardize, call it Z or Z is goal, standardize, okay? And in that case, we just need to focus on single bell curve. No need to look at many bell curve, just only one. And this is important old days when you don't have computer, right? The main bell curve, then you have main table, right? But then you just normalize it, okay? Then we just only need to look at single bell curve. This is called standardized normal, okay? And later if it's Excel, you'll be there. I think it's norm.s, yeah, something like that. So you will later see, this is important. We look at the tables, okay? Okay, maybe I should have a break first because it's now 11:15. So let's have a break first. We'll come back. We'll look at the table. We'll check table. I'll do this, and we'll talk about the rest. Okay. So, then the break time. You're welcome to do the U reply. So we will resume at 11:32. I go on to see if you have a question, but you can always type the question in the reply.
Sleeping this. That's very sleeping. It's getting cooler now. Yeah. So people get more sleepy, just like cold blood animal.
Yeah. Check.
You can read it, but it shouldn't be like
That is the PowerPoint. It's the.
okay. Okay, feel free to do it. Just look around to check it very easy.
Jesus，都係高燒定係
高燒。
你幾時去讀書？
就係月型流感，行嚟都錄得你，個禮拜5分裂。
去邊啊？咩？做日播嘅。小慧，
依家就比較少嘅啫。純粹咁樣諗嘅啫。哦，喺呢個哇，咁俾面嘅，跟住其實3得啦，都係要嘅，係最係啊，
有所有嘅係，
少啲好，少啲好。
有應該我同佢打公文打嘅態度，我冇打態，係咯，好尊重，好正式嘅啫，非常正式啊！我諗係班最正式嘅，我好耐冇見過人打態啦，會唔會好快啊？仲係。正常覺得快嘅，有人覺得好慢，有人覺得好快，係好正常。冇意思，真係唔好意思。好多人投訴我太慢，我係收到 constantly 嘅 email 係比較咁慢。我你一嚟到要同你知我搞乜嘅咧，我
OK，跟住咧，睇就
有一段最簡單㗎啦，我已經冇咁多廢話㗎啦，我已經係嘥最少廢話。已經係最精簡㗎啦。
我去邊啊？
即係會睇
真係冇得解嘅，因為我成日都唔去解釋㗎，成日都冇學過點樣解嘅。呢條嘢就係唔使記㗎，都唔會記到啲乜，我寫都寫嘅，我唔識啊，記唔到㗎，記唔到㗎。如果唔係搞啲科學嘅，你個基本就識睇嘅。有我查表嗰陣，
啲仔唔使計，
會唔會黑咗㗎嘛？你睇綠色嗰啲得咯，綠色就係會考，我要問咗我要先。藍色係嗰啲，藍色係嗰個內，綠色係個問題。咁你熟色嘅話，咪即係識咗藍色㗎啦。
我呢個都係算係，但係我冇話呢個嗰個唔係啊嘛。個 data 俾個 data 嚟先係，你唔好話叫你呢個 random variable 係多曬咋，係嘛？拍到嗰啲就唔睇你嘅，拍到嗰啲俾啲 QFN 嘅同學話我太簡單咁解嘅，俾面佢睇睇，都全部都有齊帶嘅，全部都齊帶。係啊。咁綠色格點樣嚟啫？綠色格先嚟噶嘛，係咪先？邊度唔明？咁你真係要問咯，你唔問解釋。紫色教嘅解釋啦，綠色教嘅解釋。
你話
我唔得啦 reason， 好多都唔得啦 reason 啦，係幾多咩科啊？攞係諗啦，攞點樣嚟咁諗？係嘛？你唔係讀今日攞嘅，你唔識攞點樣寫？咁話你就話呢個係咁就咁噶啦，係嘛？你話客觀大人，我而家呢個得唔講啱。有啲冇 reason 㗎，咁點解有啲係佢寫二啲喎？有啲係冇 reason 咧，係嘛？咁佢都係 arbitrary 㗎嘛。咁你又點解？我唔得嘅，拉錯交嘅真係。你可以俾我哋消息講翻佢啦，咪？咁啊唔講啦，你明㗎啦。有啲嘢就唔可以講㗎嘛，唔解釋㗎嘛。點解釋嘅 law 係唔係我都有做研康嘅 law 咁，我初到前 law 㗎。我有做 law 㗎 ，antitrust 啊嗰啲啊，全部 business law 都有㗎。有啲嘢冇得解嘅，因為 B school 更加之好就冇得解㗎啦。呢度問下你，唔會問下你個 idea 就會 work 㗎，個貓笑嘅咁樣 work 就 work 㗎啦。如果你唔知道嘅話，你係要慢慢講得到。唔係我哋學到嘅，唔係你而家學到嘅嘢嚟嘅。如果你乜都要了解到，冇人同你背嘅，你知道呢嚿嘢咁樣用就得咯，你就知道咁用就係做到 app 咁啫嘛，你撳個掣呢個 app 出嚟，呢個情況呢個等於你好多 Google 撳個掣 search 咁撳到，你知道打個 keyword 佢咪有 generate 㗎啦，或者好似 AI 咁，AI 嘅我明嘅，即係你明點用啫，我冇話佢咪點用我啫嘛，哦，你知唔知呢嚿嘢個 normal 喎？乜喂，我哋真係做唔到啊！我其實你知啊，我都係得你唔知㗎，你要精嘅。如果唔會咁解釋㗎啦。你如果明白呢嚿嘢係乜嘢，即係我意思係你明白呢個知識係乜嘢嚟嘅，落出點樣用，就係等於你要多啲。我個目標已經夠㗎啦。再叻啲咪睇埋啲即係佢啲客嗰啲證明咯。如果你要睇嘅話。就跟住睇人嘅思想，你花寫乜嘢，或者咩啲咁嘅嘢
問你都有嘅，即係
如果最難就咁啦，冇得學就得嘅。後面呢啲即係冇資料嚟，即係話如果你做呢個嘢就會 follow 呢個資料，呢個係冇資料嚟嘅，我哋就係教嘅。有啲 program 即係 algorithm 就係話有啲係嗰邊 estimate 嘅話，好夠冇錯，做嘅，你中意咩？都係啦，都係快嘅，follow 住嘅。好似 law 咁啫嘛，你想聽，你要 follow 嗰啲公式價值咁寫嘅啫嘛。點解咁樣寫冇人解釋㗎？點解擺假法咧冇解釋嘅？係咯，有得解咯。係用咗天。唔係即係你啲問題。我都係，我仲喺度揾咯，快啲咯，你做 copy 你哋佢跟你自己攞有關就跟你攞嘅問題。冇問題，所以我哋睇緊理解嘅嘛，呢個都學你嘅。因為是做
另外一題。
問題。
記得要咁太細啦，都
夠點解啦？就係
金屬嗰啲真係好啱我哋嘅。我覺得金屬，我覺得最啲好睇啲。我唔知點樣搞下面嗰條帶啊，哦，條要老練少少，係，我唔知道點得嚟咯，唔知道做好耐，係啊，就少少，我中意皮質，
咁長有啦嘛，嗰啲真係犀利。年青人
哦，係最多係食上邊，八加五加九，我背咯，記得啊，風雲唱，風雲嗰時我又唔識做，我幾少咯。嗰隻咁長，其實都係識地字嘅，都唔係嘅，因為有
又唔係一定要有啦，
係啊。之後就想睇上啲係啊，但就唔長咩咁，佢有好多嗰啲 distribution 啊嘅 formula，撳一撳地啦，咁樣啲
識嘅咁比較
長嘅，加上。我都揀嗰一排嘅，
都可以擺電腦，嗰啲 case 嘢，我都幾好呢個運動，誒幾好呢個嘢喎，都可以。
對我嚟講幾大啦，
都好大，係啊，攞埋呢個品味幾好啊，好 taste 好 taste。
成日都咩？附近有十完嗰啲咧，好鬼大部，
佢唔係有呢啲，有呢啲真係好多。
係啊，
幾多咁多嘅，或者個 iPad 首先
其實我都諗過係直接 iPad 裝 VM 用 Windows 嘅，有啲可以 run parallel desktop 嗰啲。我會試下嘅，但係有部電腦個 keyboard 係舒服啲嘅。
我就自己都冇 iPad 嘅，我梗係就咁 iPad 就擺到度。
咩係
擺落去
呢個我對我哋嚟講好緊要。
我睇字都好少寫字就係太過慢。然後我唔教書我都唔會寫字，我淨係教你哋我先寫嘅呢個字，所以我都寫字寫咗好似小學生寫字，因為我都冇寫過。咁樣我霎時間打個圖出嚟咁，但10幾年冇寫嘅字，冇寫字。呢個都寫字嘅都好啦，我覺得一支筆寫都唔好慣嘅都，幾好寫啊！不過算得出係咁樣有啲執筆，我打就打到中文又係，我都識打，但係我已經唔識寫字，中文唔識寫啦。我打倉頡打到，我已經唔識寫。我用粵拼㗎啦，佢都用倉頡嘅。倉頡但係我已經唔識。而家會試人用倉頡嘅，已經唔識寫中文字，但我仲可以打出嚟。就係咁。我覺得你識倉頡，你識拆字就倉頡真係快，真係好快，但係我已經唔識寫啦。諗下先，即係打倉頡都會識寫嘅。你唔記得個字點寫？我會㗎，會，因為你會識拆。識寫細記咯，但係你記到一次嘅字咩？我諗下對題2+3嘅話，你頭先中間寫嘅。而家我諗點打？獅山獅啊！好雜嗰啲麻煩嘅，係最麻煩。識打英文嘅應該係學寫粵語啦。講寫粵拼嘅音嘅，一定係容易啲啦。
對，我要
Alright, let's see.
入唔入到？佢冇話
Let's see what you're saying. Oh, why it takes longer time from North Point into Thailand? Okay, very sleepy, but not because lecture. Okay, because of weather, I understand. Starting to get cold, you feel very sleepy. Well, normal. I also feel very sleepy today, but I still awake because I have to teach. So you have to you are sitting, so you can be very sleepy. For homework or exam, as long as it's right, then you get credit. But if you are wrong, then if you don't give anything, you can't get partial credit, right? So I recommend that you write as many steps as you can. And if you ask me what would be the minimum required for the thing, I think my slide is already showing the minimum steps. Of course, you can skip some, but I think that is at least you should keep the first and the last step, right? If you want to do it for assignment homework. I don't know. No. I guess for the moment, I think it's open. Just bring the cheat sheet because I still can't find out the way to jam your laptop or Wi-Fi because the Bluetooth thing. Unless I have a way to jam your Bluetooth, so you might have to bring out your print copies. Because of the incident that even though it's in airplane mode, the Bluetooth can still communicate. So, and the incident that not in our class, that there's some cheating happened. Then the class had to retake the exam again. So I don't want that to happen. So for the moment, I don't know how to do it. If we do it the exam in the lab, then probably it's possible to lock down the browser, but because you bring your own iPad, then it's easy. So for the moment, unless we get a jamming machine from the IT, so yeah, I mean, there's no choice. You have to bring your stuff. Okay?
How large is the cheat sheet?
So unlimited. So you can bring as many as you want. As long as you don't share with your friend, that's fine. You bring your thing, no matter how big, doesn't matter. Okay? Infinite amount. Okay? Hungry, yeah. I try to be fast, but yeah, everyone knows first day. Is it really cloudy? Okay, interesting. The speed. So most of you think is okay speed. I do see some complaint is very slow. Okay. I do understand. For you, if you have learned probability before, it is very slow. But we have to cater for the median, so it looks like some of you will think it's too slow, some too fast. But don't worry, because of we will do this again, and assignment will help you for those who feel a little bit too fast. But do remind you that even you don't take this section, you take the section from other lecturer, the coverage material is the same. Maybe some little bit slightly different, but all the major material are the same because you use the same textbook, right? So it's not I particularly fast or slow. I make it more difficult or less difficult. Just the way we explain the thing or how we interpret stuff, but otherwise the material all the same for all the class. So even if you go to other section the same. So and just to remind you, one thing is you do a stat class. It is very normal. Something that you don't understand. This is given as a telling you this tool, how to use it. We don't explain clearly why this is true and how we come up with this tool. It is there exists the tool for you to use. Just like drill or your app in your phone. You don't know the mechanics behind. You just need to know this is the input, this is the output, right? You know when to use this tool, then that's it. If you want to know the mechanics, more detail, why this tool work, that have to go to engineering, right? So that is go to the stat department to understand what they, or advanced class. So I don't think any B school would cover that thing. Most likely we just tell you how to use these tools, what the usage, how to use them. That's it. And how to use it, example, right? And of course, you look at, I have 200 slides for this topic, maybe a lot, but do remind yourself that the only thing that you want to look at again is the area with the purple color, right? The reference, and the green thing is just the green example with the thing that you would be needing for your assignment, for your preparation for the test. Okay, another joke. Conan go to where when he's sick? Okay. Old joke. We have Tokyo, we have Nanjing, we have Beijing. Why no Xijing? Oh, that's a good one. I haven't learned that.
That's a classic.
I didn't know this joke. That's good. Wow.
Switch it to be a joke.
Wow. Oh, this is good. You make us read that thing. That's good. What do you call fish with no eye? I don't know. Sorry. Oh, that's good. That's good. That's good. I didn't learn that. Thai eat prawn can ya. Oh, that's good. That's good. That's good. Okay. Prawn can is what? Prawn. Okay. Okay. Super sad. Super stress. I hope it's not our class. But hopefully you get happier. If this is our class, I hope you get happier after the class is over. Okay, that's good. Healthy jokes. Okay, there's a joke. An example. Okay. Anything you see is the IQ, your weight, your height, and most of stuff either if you assume uniform or assume normal. This is a very typical thing to do. Okay, for discrete, the normal thing is like you want to have a uniform, right? And for continuous, you just usually start with normal or uniform. So because later you will see many things is basically normal. Okay, there's a reason behind it, but this is we'll cover when we talk about two topics later. We'll clear why all of things are normal. Okay. Okay. And the bell curve is very normal, right? When we ever try to give exam, many teachers will tell you the curve is normal. Okay, but of course, we go to B school, and CHK usually is not very normal. It's like skew on the left, right? Because many people are very good. So, but normal is so common in general. Okay. And some of you express during the break. This guy is crazy. Yeah, I agree. I mean, I never remember that guy. Okay, I put there. I said it just to make you know this guy is normal, not asking you to remember or anything we use. Because what we do is we look at what we call the knob Z table. Okay, the Z table is look at this guy. Okay, we will go to the web to show you that many Z table, and we will use it. Okay, and look at the web. There are usually the two versions of the Z table. Okay, one is focused on negative value, one focus on positive value. Okay, because the graph is symmetric, so we don't need to either version will work. Okay, the reason is less than negative value I think it's type. I think it's wrong. I think that's fine. Yeah, that's fine. No, that's fine. This is correct. This is saying this. This is saying this is 0. Okay. Negative Z. Okay. It's this guy. Yeah. It's this guy. And you can look at Z here. Okay. And look at the blue one. Okay. Okay, this guy. And this guy is this guy. Okay. And because F is symmetric about 0, so if you find the red, it's same as 1 minus blue, because 1 minus blue is purple. Okay. So I hope that is, I mean, you'll be clear because we will do example together. Is that clear? So don't worry, we will do example one by one, and then you will see how we do it. So this example, okay, we will look at in set table, go to the internet, look at the set table, and figure out all this. Okay. So the first question is Z less than 1.4. Okay. So what I do is I go to Google or Bing. Okay. Look at set table. So set table, there are many. So this one, I don't know if you can see it clearly. Let me click on that. This one focus on the negative side. Okay. We can look at this one. Or another one is this guy. Look at somewhere in the middle. Okay. But we just use this one, maybe, because pick this one is easier. Okay. So there's another one. Okay. But they're the same, regardless of what you use. Okay. Let's look at this one. Okay. The question is Z is less than 1.4, right? But the table we give is negative. So how can we do that? Right? How can do that? So it's easy to think in this way. Let's draw a diagram. Then make your life easier. So let me do this here. So the question is this. Bell curve 0, 1.4 is here. Okay. The question asks this guy. Maybe use some color other than blue. I want a paint area, right? We want the probability that Z less than 1.4. You ask me why you want to care about this. You'll be very clear later. We'll do this all the time for the rest of our course. So how to do that? The data we have is, how do we do that? We do it by looking at, sometimes we want to figure out this, but we can look at the other way around, look at the orange area, right? Because orange plus pink is 1. Okay? The orange is what? Z more than 1.4. Right? But this orange, by symmetry, okay? We know this is same as, I have a green here, negative 1.4, the green one. Is that clear? Is that clear what we are doing? So let me repeat, because we are doing this all the time. So I just have to be slow here, because this is, from now on, most of the thing we do is not procedural stuff, right? There's procedure you need to follow, just apply the different scenario. Okay. So the procedure is looking at the Z table. Okay. How do we do that? We're asking the probability less than 1.4. Okay. And the complement is more than 1.4, right? You want to look at the purple, then the complement is orange, right? 1 minus purple is orange, or 1 minus orange is purple. Okay. To find the orange, look at the flip side, the green one. Okay. So the green one is exactly from the table we have just saw, right? The table is given negative number, negative 1.4. Okay. So that's how we work on it. Let's see. Okay. So we want to negative 1.4. Okay. So this table usually you can see, I don't know whether you can see. Maybe I make bigger. Okay, this is a table. Okay. And say, how do you understand this table? Take an entry here. Okay. This entry is what? This entry is negative 3.63. Okay. Look at the row first and add up the column. Okay. This is negative 3.63. Okay. So that's how you read the column. Remember, what we want to read is 1.4, negative 1.4. So we just go down. The answer is this guy. Okay. 0.808. Okay. Okay. So let's compare it to our answer, right? Remember, this is just the area on the left hand side. You need to subtract by 1 because this is just the orange area. Remember, the table only show the green area, right? The green area equal to orange area, and you subtract it from 1, you get the purple area. Oh, the question asks you purple or the pink area, right? So let's go back to the slide. That's how you get this guy. Okay, 1 minus this guy. Is that clear? Okay. So the next thing is less than, or maybe I look at our table to give you some idea how we do that. Sometimes you're given this table. It doesn't matter. I think it's okay. Negative 1.6, negative. Okay. So this will be directly our answer. Okay. Because this table is exactly negative 1.6, right? That's this guy. Because negative 1.6 here. Okay. It's 0.5. Okay. That's how you get it. Okay. And maybe some of you look at the calculation is slightly different from, because this one looks at use this one. Okay. If the table is not a positive number, this is, I think this is the one I use it for my slide, right? So if that's the case, less than 1.4, right? You can just go down to here. This is the answer. Okay. So for convenience, usually you can keep 2 tables and choose the one that is easiest. You don't need to move around, right? If you will use this one directly, right, then you can figure out the answer. Okay. So obviously in Excel, later you will see these two tables will combine to one function. You can just do it and done. Okay. Is that clear? So don't worry, we'll do it all the time and show you to you. Okay. And so how to do this? 1.6 and 1.4. The easiest way always, as I do, just draw a graph that make your life easier to think. 0 is here, okay? And you have negative 1.6 and 1.4 here, right? So what we want is this guy, okay? So how do we do that? Okay, one way to do it, according to this one we're here, is we have take the blue area, okay, subtract the green one, right? Take the blue minus green, right? We're done. Okay, and blue is easy. It's actually from one table. Green is also easy, also come from the other table, right? Okay, look at the blue one first. The blue one can rely on the table. From this table, right? It's a table 1.4. Go to here, 0.9192, negative 1.6. Come from this one. Go to down here is 0.548, right? Or this is already calculated in the first 2 bullet points. Just do a subtraction here. Is that clear? So you can use single set table or use the both set table. It will do the job. Is that clear? So why you need to look at the set table? Because that is what you will be bringing to the test, because you don't have access to your computer. So that's why you need to talk about that. Okay? Is that okay? Don't worry, we'll give you a chance to do it. So this is the diagram that I mentioned. All right, this is how I draw it. So next is very useful rule. That is probably the one of the very useful thing that you learn from a bell curve. It's called the rule of thumb. Okay, and as I said, many things are from normal. So, and that actually explains why you would care about standard deviation or variance. Is it turns out for a normal, 70% are actually within one standard deviation, 95 within 2 SD, and 98 become 2 SD, right? So that means that 2 standard deviation is the main deviation for the data you have. Right? Later you will see that is how we're trying to do our data. Right? Usually we predict the mean, right, with a sample mean, and we'll plus 2 minus SD will be our interval estimate. Okay, that will be something we'll talk about next class. Sorry, next class onward. That is a 2 SD thing is very important. And later we'll do hypothesis testing. Okay, we'll try to say whether the sample mean is supporting your hypothesis, is whether it's within 2 SD. So this idea is very important. But at least you know, for Bell, most of the things actually appear within 2 SD, and that is very useful for most of our application. Okay, and likely that actually this is the thing that if you don't do deep statistics within 2 SD, is the rule that you often use. I mean, and the 3 SD is 99%. Okay, so sometimes you look at called the 3 sigma rule, or called the 68, 95, 99 rule. Okay, and now it's not that common, but in my day, there are famous book called 6 Sigma, and I don't know where still you heard about that. Look markup, but anyway, it's a very interesting thing. Okay, so this is the graphical representation of the empirical rule, and this is the rule that are very useful. Okay, now the next use of table is to use this inversely. Okay, so we often do this is we want to reverse it, right? Before we are saying if the bell curve, I give you some number, what's probability between that two number? Now reverse it. I give you what's the probability that I give the probability say 0.5. What is the Z? Okay, will locate such that the probability is 0.5. Okay, so to give a more concrete thing, that's a question. Okay, what's the probability that such that Z less than small z is 0.95? Okay, graphically mean this. Okay, just reverse what we are doing. Okay, here are a bell curve. Z, I start from 0 here, right? The question is the following. I have an area, okay? I tell this area is 0.95. I go to the area and ask, what's the number here? This is the question, right? Before I have a reverse, I ask the number below, ask the area. I give the area, ask the number. And why it's important? Because later you will see this give us a lot of calculation that we need. Okay, and this is a lot of application, so I'm not going to explain, but this is the thing we need to do all the time. So how do we do that? Okay, this again require reading from a table. Okay, so 0.95, how to read the table? Go to this table. Okay, look at 0.95 in the entry and go back. Okay, and you try to scan it out. 0.7, 0.8. Okay, 0.95 is somewhere here. 1.6 between the fourth column and fifth column. Okay, 1.645. Oh, by the way, how you get this slide in your you can just basically, I think you can just type C table and type dummy, and Z table and dummy. Then I think the first outcome, Z table and dummy, the first one will be the table. Okay, but of course later when we talk about Excel today, you will see we can construct them. Okay, if not enough time, we'll talk about tomorrow. I mean on Friday. Okay. Okay. So now a lot of procedural stuff. Okay, but we'll be doing that all the time. I'm sorry, but this is something that we can't skip. Okay. So the question will be the following. Okay. Now I have a random variable x that follow normal distribution with mean, mu, and sigma 16. Okay. So I want to calculate x is less than 16. Okay. So the idea is the following. Let's draw a graph to see how we do it. Okay. So the question is the following. X here, a bell curve. Okay. And the mean is 20. Okay. Mu is 20. And we have sigma square is 16. Okay. The variance 16. Okay. And that implies one thing. Sigma is 4. Right? Because square root of 16 is 4. Okay. So the question is asked, what is the probability that's less than 1 SD, right? So it's here. What is this number? So this is the question being asked, right? And remember, When you talk about normal, we always convert to the normal. That is here. Okay, we just convert this guy. Okay, remember what I'm going to do is I basically move the mean from 20 to 0. Okay, how I do that? Z is equal to x minus mu over sigma. Okay, by doing so, I actually end up with 0 here. Okay, and I draw another graph here. Okay. And this is sigma equal to 1, or sigma squared to 1, the same thing. Okay, I have another bell curve. Okay, and the important thing here is like this. I have 16. This will be what? The transformation is minus the mu over sigma. So 16 minus 20 over 4, right? 16 minus 20 over 4 is negative 1. How to get that is follow here, right? 20, right, is 16 minus 20 over 4 is negative 1. Okay, so this is the area. Okay, so what you need to do, look at the table, then look at negative value, that's the negative 1. Right, so that's what we're going to do. Go back to here and check the table we need. So this is positive 1. Look at negative 1. So this is the table we need. Okay, we look at the entry that belong to negative 1. Okay, so we just look at this, scroll down to negative 1 is 0.1587. Okay, so that is how I get the number. Is that clear? This procedure we will repeat many times in the class because we will be doing all this for the estimation, hypothesis testing, regression. We do it all the time. So don't worry, you will be doing this so many times. Okay? So this is the idea. Okay? As I write down in the slide, right? This is how you do it. Is that clear? So the next is more than 24. Okay. So the same idea apply. Let me draw it because I think I should be very slow here because you'll be doing this again, and again. It's good to have a firm foundation what's going on. Okay. X, we have 20, the bell curve, and sigma is 4, we explained. Okay, and the question is 24 onward. Okay, so there's a bell asking this question. Okay, this is the question being asked. Now, what we're going to do, always transform to the Z. Right, this is 0 and a bell. Okay. And what's 24 here? How to transform from here to here? Z is what? X minus mu and sigma. What are we doing here? Basically, with bell, we're going to move from 20 to 0, and then use a hammer to damn, and then make it flat or more squeeze it, right? And I think it's 4. I need to squeeze it, right? Because I changed from the sigma from 4 to 1, right? So just kick the ball, kick the distribution to 0, right? And I squeeze. Okay, that's how I do. And how we do it is 24 minus 20 over 4. which is 1, right? So this is 1. So this is 1. Okay, and they're the same area. Okay, they're the same thing. Okay, is that clear? So it just calculate that area. Okay, but the table you have is always on the left hand side. Okay, so you cannot get the green directly. You will use the orange, and one subtract from the orange is the green. Okay, look at the orange is less than 1, right? So look at the orange. Orange is here. Look at the Z is 1. Go down here, this guy. 1.00 is 84. Do you remind yourself this is only the orange area? You have to subtract it to get the right hand side. Okay. So that's it. Nothing very special, right? So I hope it's clear how to get that. Okay, so that's why one subtract from that. Okay, this is the thing that we will be using all the time. Okay, so that is the graph, right? The blue is what we want to find. Okay, the pink is what we found, right? So now here comes a most difficult thing. Okay, it's asking you to have 16 and 24. Okay, so the question look like this. X 20 sigma is 4. Okay, so it's 16 and 24. This is the thing we want to look at. Okay, and when we do Z, this is 0, and this is -1, this is 1. How you get that? You subtract 16 from 20 and divide it by 4. Similarly, you have 24, subtract 20 and over 4, right? So this is the area. Right? And how do you do this red area? You take the area on the left of 1 and area of -1, which we already found, right? So we can do that. Is that okay? So this is the number we already found in the previous question. So it looks okay. Is that okay for this one?
We'll reply the email.
Okay. Now, I want to talk to you about another property that I wish to share with you. We don't do any proof, but you will see that is important. The first one is saying that if I have 2 bells and the bells are independent, adding up 2 bells is still a bell. Okay? So what is so interesting here is the following. What does that mean? It means the following. I have 1 bell. Okay? I have another bell. Okay? But it does mean adding up is still a bell. Okay? That is not true for most of the thing. You add up 2 binomials, not binomial. You have 2 Poisson, not Poisson. But add 2 normal, remain a normal. Okay, so later you will see why this is significant. Okay, and we have said the mean here is very natural, right? Because mean of the sum is sum of the mean, right? And mean of variance of sum is sum of the variance if they're independent. So this is this follow exactly from expected x plus y is expected x plus expected y. Okay, same for the variance. So, and this is same as this follow from variance of x plus y. If the independent, it's just variance x plus variance y. Okay? So the only new thing that belongs to this slide is if they're bell, end up still a bell. Okay, so this is a very unique property of bell. You try to add two uniform, it's not uniform if they overlap, right? If uniform 1 to 6, the other one is 2 to 5, then no longer uniform, right? But this is very special. Is a bell regardless of the mu x and mu y, same as y. No matter what you add, it's still a bell. Okay, it's very surprising. Okay, and even more interesting is the subtraction the same, right? Because you can make the mu is negative, and everything follows. Right? You subtract 2 bell, it's still a bell. So it's super interesting stuff. Okay, and actually that's the reason why I look at the investment, look at the stock. If you try to model stock at the normal, if everything's normal, your portfolio is still normal, right? Because adding up and subtract and so on and so forth, right? You multiply stuff, right? So that's why normal is very convenient for modeling. Okay, and we'll talk about the rest on Friday. We should be able to finish this topic on this Friday. Okay, so I'll see you on Friday. Have a nice day.
That's fine.